Well, hey everyone. Thought what we do is spend a little time talking about something called Benford's Law. Benford's Law is a really useful tool in analytics for helping us to identify data sets that have been manipulated or somehow don't match our expectations. So let's go see what this thing is called Benford's Law. So Frank Benford was a physicist working for GE in the 1920s. As he would use his logarithmic tables for looking things up, he would notice, for example, that the pages in the front of the book seemed to be used a lot more than the pages in the back of the book. And he wondered why that was. So he started looking at a lot of other different situations, and he drew the conclusion, or hypothesized, that there were more numbers in the world that begin with low first digits than those that begin with high first digits. So eventually what he found out, and we're going to see in a moment, is that these leading digits do not appear randomly as we might expect. A 1 appears as a lead digit in a number about 30% of the time in nature, and as a 9 it appears as the first digit only about 4% of the time. So we went through and looked at a lot of things like the lengths of the rivers in the world, and he concluded that his theory was correct, and that numbers do not occur randomly but have a predictable pattern. If we know the pattern, we know what to expect, and then if we know what to expect, then any violation of our expectations would indicate that there's a problem with that data, and it would lead us to want to ask the question, where's the problem and why is it occurring, right? So this is what Benford found. He found that for first digits, the number 1 occurs as a first digit about 30% of the time. The number 2 occurs as the first digit about 17.6% of the time, all the way down to the number 9 occurring approximately 4.576% of the time. So that's a really important observation. If we know that numbers have a particular behavior pattern, then we can exploit that knowledge to look for deviations from that pattern. Now, it's also true that there are expected patterns for second, third, and fourth digits. There's for 0, there's no first digit percentage. That's because 0 is never at the beginning of a set, right? The beginning of the set of numbers is always a digit of 1 through 9. It's never 0. But 0 can occur as the second, third, or fourth digit, and you can actually compute those percentages. As you get out toward the fourth digit, it does appear to be more random. It's not as precise, and actually the third digit is somewhat somewhat random as well, but certainly for the first digit and to a certain extent for the second digit, you can predict what percentage of numbers you might expect to see in a particular range. So now, there's certain things that we have to have with our data set that make this work. First of all, the numbers in the data set have to describe something of a similar phenomenon, a length, a measure, a count, something like that. Numbers do not contain a built-in maximum or minimum value. So you can't, for example, we can't have a situation where no number above 5 ever occurs as the first digit. That would be kind of strange, right? And you can't have assigned numbers for applying the Benford's Law test, because assigned numbers are always assigned in a sequential order, so assigned numbers generally don't conform to Benford's Law either. So what we can find is we can find where these deviations exist. So for instance, a CEO once began issuing fraudulent insurance policies. To keep up with the policies that were fraudulent, he used 99 as the first 2 digits. Eventually, 2/3 of the accounts receivable were determined to be phony, and a Benford's Law test would have shown that accounts with a 99 prefix actually represented 60% of the accounts receivable instead of the expected 4%. That would be a deviation from our expectations. Now, we also know, for example, that cash deposits above $10,000 or $10,000 or above that are made in a bank have to be reported to the federal government. That's a banking requirement. And so what people do is they engage in an activity that we refer to as structuring. And what they do is they structure their deposits so that the deposits never reach that $10,000 limit. They might break $90,000 worth of cash into $9,000 deposits. Now, when people are doing that, it would indicate or would be evidenced by a whole lot more deposits that start with 9 than you would normally expect. You would normally only expect 4% of your deposits to start with the number 9. But if people are structuring, then that number of deposits starting with the number 9 will go up. So, again, the conditions for applying Benford's law. First of all, the data with values formed by mathematical combinations from different distributions will work. So, for instance, if you take sales and multiply it times sales tax, that would work. The quantity multiplied by the sales price, that would work. Data with a wide variety in the number of figures helps. Data from a large data set so larger data sets usually work better with Benford's law than smaller data sets do. Data that is right skewed, in other words, the mean is greater than the median and it's non-symmetric. That kind of data works better than data that is distributed uniformly or distributed with some kind of a normal distribution. So, for example, here, if you have a situation where every number occurs exactly the same percentage of the time, that would be an indication of structured numbers or manufactured numbers. Often people, when they are trying to commit a fraud, they make the presumption that numbers occur randomly. So they'll try to have numbers that begin with 1 happen just as often as numbers that occur with that start with 2, and that happen just as often as numbers that start with 3, etc. And what you end up with is a distribution where all the numbers occur in the same frequency, and that would be an indication itself of a problem with your data. When data have no predefined maximum or minimum value except for 0. 0 can be a minimum. In other words, that's a null set, right? What kind of accounts usually are good for performing a Benford's law test? Accounts receivable, accounts payable, sales, expenses, sales discounts, sales returns, and inventory purchases are all good accounts for applying a Benford's law test. So Martin Negrini is a accounting professor who has written a book on forensic analytics, and he's talked a lot about Benford's law. He noted that it can be observed that accountants tend to round up their numbers. So, for instance, 798,000 would round up to 800,000. Now, if this is true, then what Benford's law would suggest is that we should see a lot more numbers occurring, that zeros would occur more often than 9s as the second digit in the data set. So, for instance, if somebody has like 798,000, that would round to 800. So numbers that normally would occur as 9 would occur as 800. And if you recall, in second digits, zeros occur, and let's go back and look at this. You can see here that numbers that begin with 0 should occur about almost 12% of the time. But numbers that begin with 9 should begin about 8.5% of the time. So if we see that 9 number being low and the 0 number being higher than we would expect, then that might indicate you've got some rounding going on in your data. The other thing that Negrini notes is that Enron and WorldCom data showed an unexpectedly high number of second-digit zeros in their data prior to their collapse in 2001 and 2002. So round-off biases can also be seen, by the way, in earnings per share numbers. So if we'd applied Benford's law to Enron and WorldCom back in 2001, 2002, we probably would have seen that there were some problems going on with the numbers. It's also been shown that humans are not really good at generating a list of random numbers. First of all, the numbers will have some kind of a pattern in them, but the pattern will not match Benford's law. That's been shown. It's also shown that when people invent numbers, they just don't conform to Benford's law. Often, as I stated, fraudsters often make up numbers, and they make this presumption that somehow 1s, 2s, 3s, and 4s occur an equal amount of times. It's not like flipping a penny, okay? With a 50% chance. These numbers have a known pattern of occurrence, and we exploit that pattern to get better information from the data that we're looking at. So what will happen generally is an auditor will look for deviations from those expected distributions in the tables. Okay, first digit tests are the most common kinds of tests, though we will run, as you saw, second. It's good reason, good opportunity sometimes to run tests on their second digits. It'd be highly unusual to find a set of data that matches Benford's distribution exactly. Okay, it's just not really going to happen because people's behaviors don't always behave exactly in the order that we expect them to. So the real question is whether the differences between Benford's distribution and the distribution that we find are large enough to indicate a problem in the data. So we do a test for conformance. How well does our data set conform to Benford's distribution? And for that, we're going to use either a Kolmogorov-Smirnov test or a chi-square test. Another one that can be used is a mean-squared difference test, which is the one I'll demonstrate in a example data set later. So there are tests you can use that will help you to identify problems in your data and whether or not those problems are significant enough to cause you concern. So what do we conclude? We conclude that first, Benford's law is a useful tool for identifying data that have been manipulated or falsified. The patterns can be useful in identifying where the problems in the data reside. So if you look at the Benford's law chart that you see below, the blue represents the actual Benford distributions. The red line represents the distributions in a data set, and I'm actually going to show you how I got this line. And what we can see from this is ones and twos and fours are occurring less frequently than we expect. So those are 6 and 8s. 7s and 9s appear more frequently than we would expect normally. And so the question is this resulting red line sufficiently different from the blue line to indicate a problem with our data? And that's what the example problem is going to look at.